Hello. I got a head start. While you weren't looking, I drew this picture just to save some time. Otherwise, it was going to be a video of me drawing this big picture on here, and I didn't think you'd want to watch that. So here's the picture, also known as a fig. And it's a tree. It's our first fig tree. A tree, I haven't officially defined it. Let me officially define it. A tree is an acyclic, A-C-Y-C-L-I-C, acyclic connected graph. Yikes. I got to underline all three of those words. An acyclic connected graph in which each node, maybe I should have written the definition too, has 0 or more child nodes and exactly one parent node. And I know that doesn't make any sense. This video, by the way, is all about terminology and explaining it and working definitions. They might not be technical definitions, even though this is a fairly technical definition of what the tree data structure actually is. It's an acyclic, I'll have to define that, connected, that was easy, graph, doesn't look like a graph, in which each node has 0 or more child nodes and exactly one parent node. You know what, I will put a definition down here of graph in this context. A graph, when we're talking data structures, is a set of nodes and arcs that connect them. A set of nodes and arcs that connect the nodes. Example. Well, I already got an example. We've been using graphs this entire module. A set of nodes and arcs that connect the nodes. Example, a linked list is a one-dimensional graph. One dim for short. A linked list is a one-dim graph. What is that? Oh, that was a dash. That's what it was. One dash dimensional graph. The nodes are the nodes. No new definition there. Except now instead of the arrows, instead of calling them arrows, we would call them arcs. And in a linked list, that's actually a special case of a graph, not only because it's one-dimensional, because it's what we in the biz would call directed, meaning every arc in the graph is one way. I could have done that here. I could have had an arrow from pet down to cat. But the default assumption is if there are no arrowheads on the arcs, then I can go either direction on those. And I don't even worry about implementation and stuff like that right now. I'm just worried about what the thing is. What is that thing that we've drawn a picture of? So here's an arc that connects Mutt to Solomon. And since there's no arrow, that assumes, without further specification, that I could either move in the graph from Mutt directly to Solomon, or I could move from Solomon directly to Mutt. See how we do that? Now, an acyclic. Acyclic means there's not more than one way in the graph to get to the same node from the starting point. Forget that. It means that you can't go around in a circle. I'm going to mess up my graph and then I'm going to unmess it up. Don't mess up yours. Just watch what I'm about to do. I'm going to connect Tabby to Leo. Boom! It's not a tree anymore. Why? Because there's a cycle. I can start at pet and get back to pet following arcs in the graph and not going by any node in the graph twice. That's a cycle. I can go around in a cycle. Acyclic means I can't do that. There, I fixed it. It's back to the way it was before. There's not any way I can start at pet and go through a bunch of different nodes and then end up back at pet without retracing my steps. Oh, I could recursively, oh, let's not even go there yet. But I could get back to pet if I recursively backtrack. I'm sorry to bring those words back into your foreconsciousness. But there, that's what acyclic means. Connected means that we can't have this. Fish and Goldie, Well, those look like legit nodes as much as cat and dog and tabby and precious and all that stuff, but they're not connected. Actually, we would call this a collection of connected graph components. See, we don't even want to go there. That's not a tree at this point. If all of these are nodes of the thing, whatever the thing is, and all the arcs are arcs of the things, it's not a tree, but it is still a special kind of graph, a collection of connected components. And yeah, you can flush that from your mind. We don't need to know that when we're talking about trees. It's just these are terms and definitions you're going to run into now that we are sneaking up on advanced data structures, and there's all kind of stuff. Let me see. An acyclic, got that. Connected, got that. Graph, a graph is nodes and arcs connect them, which each node has 0 or more child nodes and exactly one parent node. Well, that's going to be part of my laundry list over here of terms that need to be defined. And I am not going to write out definitions for every single one of these because no one would watch this video completely to the end, or at least I don't suspect you would. But I'm going to put them up here and talk about them. I already broke the seal on child in a tree, parent in a tree, and I will give examples of these. I'm just not going to write out formal definitions. I also need an internal node, I-N-T, gotta spell it right, internal node, whatever the heck that is, external node, path. What else we got? Internal node, external node, path, subtree, root, and there might even be others that occur to me as we get going on these. I will mess up this picture temporarily and erase it. That's going to be my style of illustrating what each of those terms actually means when we're talking trees here, when we're out in the forest talking trees. Let's see. Green, that's a nice tree color. Child, I guess I can get away with just pointing. That's not too hard to understand, I hope. Cat is a child of pet. As we move from pet down one level, follow one arc down here, then cat is a child of pet. Now actually, that's probably not the best one to start with. I'll start with this. A tree is a hierarchical data structure, meaning it does have a top and a bottom. The root, I'll even label that. Pet up here is the root of the entire tree. Nobody else is the root. There's exactly one root to the tree. Now then, now that I've done that, I can say, well, the root of this tree has 2 children. It has cat as a child on one side and dog as a child on the other side. So not only does that, I hope, give some sort of intuitive, warm, fuzzy feeling about what a child node is, a parent. Pet is the parent of cat. There, 2 checks in a row. That was pretty quick. Let's find a random node. Oh, mutt. That's a random node. Mutt is a child of dog, but Mutt is the parent of Michael and Solomon and Leo in the tree. Let me say that again. Mutt, as a node, depending on our point of view, what kind of thing we're looking at Mutt about, it could either be viewed as a child node of dog, or it could be viewed as the parent of nodes Michael and Solomon and Leo. Okay? Now, let's pick another node. Leo, way out here. Leo is a child of Mutt. But Leo has no children whatsoever. He was fixed too young. So it doesn't necessarily follow that each node is going to be a child and a parent. This one is a parent, but the pet is a child of no one. The root of your whole tree doesn't have a parent. So sometimes you have parents, sometimes you have children. You don't always have both. That's what this is trying to talk about, in which each node has 0 or more child nodes. Leo has exactly 0 child nodes. It has no children. And exactly one parent. As you're moving up in the tree, the parent is unique. There is one parent for each node in the tree, except for the very special case of the root. Okay? Who else? Here's Collie. Collie has exactly one parent, dog. It looks like there's a lot going on here. Well, Mutt still. Mutt has exactly one parent, even though it has several children. Leo has exactly one parent and no children. So that's what that description is talking about. Each node has 0 or more children, exactly one parent. Internal node means you got kids. an internal node has at least one child node. Cat is an internal node because it has tabby, a single child over here in the graph. Dog is an internal node. It has 3 children, pug, collie, and mutt. If you couldn't read those. You know what? I should probably read the labels in case you hadn't been able to read those. Pet is at the top of the whole thing. It has 2 children. Look at the terms I can already use. 2 children, dog and cat. Dog is the parent of pug, collie, and mutt. Pug is the parent of Oscar. Mutt is the parent of Michael, Solomon, and Leo. Over here, cat is the parent of Tabby. Tabby is the parent of Precious. And you've already figured out your own definition of external node, but I'll go ahead and talk about it anyway. An external node is a node that doesn't have any kids. It's down at the bottom. Also known as the frontier of the tree. It should be a nice word for us since we're all pioneers. We're interested in the frontier. The frontier of this tree, all the nodes that don't have any kids, would be Oscar, Collie, Michael, Solomon, Leo, and Precious. Those are all external nodes. Okay? We're almost done. Path. A path is just a sequence of arcs, or sometimes it's described as a sequence of nodes. I don't have any labels on the arcs here. I don't have any name for these arrows or these lines here. So I guess we'll have to think of a path as being something like pet, dog, mutt, Michael. That's the path from pet to Michael. And it has length. Here we do count the arcs. It has lengths 1, 2, 3. Length 3. 3 arcs in the path from pet to Michael. Now, another defining property, actually an alternative definition for a tree, is to say that it is a connected graph in which there exists exactly one path between any 2 nodes. Eeny, meeny, miny, I'm going to pick Tabby over here and Oscar. There's exactly one path. I have to use some of the arcs going backwards, kind of, but I can go Tabby, cat, pet, dog, pug, Oscar. That path is unique if this is a tree. If there were more than one way to get from Tabby to Oscar, then it is a graph. It's still a graph because it's nodes and arcs that connect them, but it would no longer be a tree. I'm saying the same thing several different ways now. But when I had that arc, wherever it was, between Tabby and Leo maybe, then that wasn't a tree because there were 2 ways to get from Leo. There were 2 paths, pet, cat, Tabby, Leo, or pet, dog, mutt, Leo. And I beat that to death. That's a beaten path. Gone. Subtree is kind of a weird idea. Let me pick an interesting node here. Dog is an interesting node. Of course it is. The subtree, here's how we would describe it. It's if we cut this right here, this arc that connects dog to the rest of the tree on the other side, and only focus on dog and all of its descendants, all the generations beneath it. This is called the subtree rooted at dog. You might say, well, dog's not the root, pet's the root. And you would be right. The root of the subtree here is dog. Now, dog is not special that way. Mutt is the root of its own little subtree. Mutt is the subtree rooted up. No, I've got that backwards. The subtree rooted at mutt has mutt, and then the children, Michael, Solomon, Leo, all of that together in the subtree. Precious. Poor Precious. No subtree. Yet. Precious is her own little princess here. Precious is the subtree. Precious is the root of the subtree rooted at Precious, which has exactly one node in it. You could be a subtree all by yourself if you don't have any kids. Michael's a subtree all by himself. Michael is the root of the subtree rooted at Michael, and that's all there is to it. Pug is the subtree root of the... I'm not going to be able to say that once correctly in this entire video, so I might as well give up. Pug is the root of the subtree rooted at Pug, which consists just of this right here, Pug and Oscar. It's Pug and all the descendants below it. Dog and all the descendants. Here's another bigger subtree. I'm messing up this picture because we're almost done and I don't have to erase and fix it anymore. Subtree and root. We talked at root all over the place. Root is just the top node. Think of it this way. The root is the top node that you're talking about right now. We're kind of almost just shutting off part of the tree. When I look at the subtree rooted at dog, then I'm kind of shutting off all the rest of the tree, and for all practical purposes, I can think of dog as the root. It's the root of its own subtree. Move this direction, Pug is the root of its own subtree, and I don't care about what else is going on in the tree. So root is a pretty flexible term. That can be applied at any node in the tree at one time or another, depending on where we are and what we're doing with our data structure. All of these, is this everything that I was going to talk about? All of these are just terms that we need to know so that we can discuss amongst ourselves intelligently about trees and all those sorts of things. And I think that'll do it for now. So that's it for terminology. See you online.